In this lecture, we are going to discuss the mechanism nucleophilic substitution. So the word nucleophile is made up of two words, nucleo and phile. So the word nucleo from the word nucleus. So the nucleus is positively charged. Then phile means loving. So it means positive charge, loving. So it means a species, for it to be able to be attracted by a positively charged center, so a nucleophile should be electron rich. So by definition, nucleophile, it is an electron rich species seeking electron deficient center. So it is attracted by an atom which is electron deficient with a partial positive or with a net positive charge. Then the word substitution. So in a substitution reaction, it is recognized by the ability to maintain the degree of saturation. So in nucleophilic substitution, we are going to come across the structures of halogenoalkanes. So we've got primary structure. So it's a primary if the carbon onto which the halogen is bonded to one carbon, like this one. So this is a primary structure. Then we have a secondary structure, a secondary halogenoalkane, if the carbon onto which the halogen atom is bonded to two carbon atoms, like this one. Then we have tertiary, if the carbon onto which the halogen is bonded to three carbon atoms. So halogenoalkanes are able to undergo nucleophilic substitution because the halogen is more electronegative. So we've got the halogen is more electronegative. So the carbon is electron deficient. So the bond is polar. Then therefore, since the carbon atom is electron deficient, this carbon atom is electron deficient, so it is easily attacked by nucleophiles, which are molecules or ions having a lone pair of electrons. So examples of nucleophiles, we have hydroxide, the lone pairs on the oxygen. We also have cyanide. We also have H2 water. We also have ammonia. So the mechanisms, we've got two types. So we've got the SN1 and the SN2. So we are starting with SN1. Starting with SN1. So SN1 meaning nucleophilic substitution, unimolecular. Alright, so in nucleophilic substitution, SN1, so this one is mainly for tertiary. It is mainly for tertiary halogenoalkanes. So the mechanism has got two steps. So an example of a tertiary halogenoalkane is this one. So the first thing we have to put dipoles. So halogen is more electronegative, partial negative. This carbon is electron deficient. So because of the bulkiness, so this bond will break. So this reaction is the rate determining step. So this is slow. So we get a tertiary carbon cation. But the carbocation intermediate is trigonal planar because this carbon becomes sp2 hybridized. So this carbon becomes sp2 hybridized, so it will be trigonal planar. The next step is faster. So in the case, let's say our nucleophile, we have hydroxide. So let's say we've got the hydroxide as the nucleophile. So the first reaction was slow because it involves bond breaking, but the second step is fast because it involves bond formation. So during first step we lost the halide, so we need to add halide here. So we have to add the halide, so it's plus x minus. So by looking at the first step, which is the rate determining step, we only have one molecule. This molecule is only participating in the rate determining step. So only the species participating in the slowest step will appear in the rate equation. So rate equation, so rate equation, so rate is equals to K multiplied by concentration of the reactant which participates in the rate determining step. So this becomes C4 H9X. So this reaction, so it means, so since we only saw the overall order, so overall order is equal to 1. So the rate of reaction, so kinetics only affected by concentration of halogenoalkane only. Since we only have the halogenoalkane in the rate determining step, so the reaction is first order. Then let's look at the energy profile for SN1. So it looks like this. So first step with the highest, so the first step with the highest activation energy, so which is the slowest step, then activation energy for the second step, which was fast, so the activation energy is lower. So this is the energy profile. Next, let's look at the SN2. So SN2 means nucleophilic substitution by molecular, and this is mainly for primary halogenoalkanes. So an example, so the mechanism goes like this. An example of a primary halogenoalkane is this one. So as usual, this carbon is electron deficient. This one is more electronegative. So we put a curly arrow, but the nucleophile hydroxide you attack from this end, then we get, so this, we only have one step in this reaction, so we are going to form a pentavalent activated complex. So it will be like this. So that's the pentavalent activated complex, and it is negatively charged. So that's pentavalent activated complex. Then it proceeds to give us the product. Plus halide. So we only have one step here. So, but it passed through the activated complex. So the rate of reaction, the kinetics, so it will be rate is equal to K multiplied by, so we now have two species. So we've got the hydroxide, which is acting at the nucleophile. Then we also have the halogenoalkane. So we have two species participating in the rate determining step. So in this case we have, okay, we have hydroxide multiplied by the concentration of halogenoalkane. So overall order is equal to, we've got one hydroxide and one halogenoalkane, so the overall order is equal to 2. So the rate of reaction is affected by, so rate is affected by both, so by concentration of halogenoalkane as well as concentration of nucleophile. Then the energy profile will look like this. So this is the energy profile for SN2. We only have one step, and at the climax of the energy profile we have the activated complex. Then why tertiary halogenoalkanes? Why tertiary halogenoalkanes? So why tertiary haloalkanes? Under favor SN1. So number one. Okay, so because of three large alkyl groups surrounding the carbon, so we have steric hindrance. So the first one is steric hindrance. So the bulk alkyl group will inhibit the nucleophile to proceed under SN2 due to the bulkiness of the groups. Then the number two, where the tertiary carbocation, so the tertiary carbocation, intermediate is stabilized through inductive effect. Compared to the primary carbocation. So for example, okay, so if you look at the stability, so for a tertiary carbocation, it will be like this one. So we've got an alkyl groups. We have three alkyl groups. So compared to this primary, so we've got three alkyl groups. So an alkyl group is able to diminish the electron deficient on the carbocation, the electron deficient carbon, by donating electrons through inductive effect. But in primary carbocation, we only have one alkyl group. So in terms of stability, the tertiary carbocation is more stable. Therefore, formation of the tertiary carbocation is more exothermic. So then the primary is less stable. So it cannot be formed via SN1. Now, this person will deduce the structure of the halogenoalkane and the mechanism of the reaction. So we have to start, for example, we can start the effect of concentration of hydroxide. So studying the effect of the concentration of hydroxide using experiment B and C. So we're going to say 0,2 divided by 0,05 to the power of n is equal to, then the rate is 4 times 10 to the power negative 5 divided by 1 times 10 to the power negative 5. So we're going to get 4n is equals to 4, implying that the order of reaction is equal to 1. Then to start the effect of the concentration of the halogenoalkane, in this case I'm going to use the experiment A and B. Alright, so but the concentration of hydroxide is not fixed, so I'm going to use the another method. So I'm going to say 0,2 divided by 0,1 to the power of n, but we already know the order with respect to the concentration of hydroxide, so I'm going to say 0,2 divided by 0,1. So the order is 1, so it is equal to 4 times 10 to the power negative 5 divided by 1 times 10 to the power negative 5. So this is equal to what? Is equals to 2 to the power of n multiplied by 2 is equal to 4. So 2 to the power of n is equal to, so 4 divided by 2 gets 2. So implying n is equals to 1. So it means the order of reaction with respect to each reactant is 1. So rate equation, so rate is equal to K multiplied by concentration of C4H9Br multiplied by concentration of hydroxide. So this means the halogenoalkane is primary. This means it is a primary. So it's a primary halogenoalkane. So the mechanism, it means, so it's either, you can choose, so it's either the structure is this one, okay, it's okay, so C2H5 C oro, we can have these compounds still they are, or you can have C okay, no, okay, so okay, all right, this one, 1, 2, 3, 4. So we can either have these structures. Then for the mechanism, it undergoes what? SN2. So we can proceed via SN2. Alright, then in this question, describe the reaction mechanism for reaction 1. So this structure, we've got an alkyl group. We also have an alkyl group and another alkyl group. So it means this compound is tertiary. So for a tertiary halogenoalkane, it undergoes SN1. So in this case, we are going to say CH3, then Br. So get the carbocation intermediate plus bromide. Then we are adding hydroxide. Okay. Alright, so that's the mechanism for reaction 1. We can meet in other lessons. I thank you.